I'm James Festmeyer, Chief Architect for GenH2. At the heart of the hydrogen economy is the ability to design, build, and deploy equipment to put liquid hydrogen to practical use. We're happy to be a part of the DOE project with the consortium led by Shell, with CB&I Storage Solutions, with NASA Kennedy Space Center, University of Houston, and GenH2.
My name is Marco Guerrero and I'm from Chihuahua, Mexico. My role in GenH2 in this project is as a project engineer. There is a large project led by the Department of Energy and Shell in which GenH2 is involved. This project focuses in the development of the largest liquid hydrogen storage tank. To develop this tank requires a high level of engineering since this is something that is never done before. This project allows GenH2 to be one of the main contributors for the future of liquid hydrogen infrastructure. Right now, I'm located on the top of the simulation test platform, and behind me, I have the CRAT CS900. As you can see right now, we have vacuum jacketed lines that allows us to fill in the coal masses or tanks inside there safely. At the same time, we have vacuum jacketed lines on the other side that lets us vent the cryogenic liquids in a safety manner. Now, the CRAT 900 divides into two main parts. We have the lid and the body. As you can see, the lid contains several different ports. Some of those ports utilize instrumentation like thermocouples. Thermocouples let us know the temperature inside the vessel at different points. Also, we have vacuum gauges that tells us the vacuum level inside the chamber. One of the features that make the CRAT CS900 very special is the capability to take different coal masses or tanks, for example, unmanned aerial vehicles or single chamber or 3 chambers. Another feature of the simulation test platform is the capability that allows us to separate the vessel from the lid. We utilize this capability to be able to change the tanks, the coal masses, or also the test specimens inside there, and we're gonna demonstrate it right now. Right now, what I'm doing is I'm opening the valves that will feed the liquid nitrogen to the coal mass inside the vessel. Right now, what you can see is we have boil-off, what we call boil-off. This happens with something very cold gets in contact with something very hot, like liquid nitrogen right now, it's at 77 Kelvin, and the ambient temperature is around 300 Kelvin. This creates a heat exchange between it, making the liquid evaporate. So think about it like boiling water, basically. This is part of the preparation for an actual test. We call it the cool down. The cool down happens before we actually filled up the coal masses with liquid. Why? Because the coal masses right now are at ambient temperature. So before we can even fill it up, we need to cool it down utilizing the same liquid. That's why we have so much vapor coming out on the back, because it's getting in contact with all that heat inside the vessel while the liquid nitrogen is actually trying to cool it down. Right now, I'm gonna open the vessel so you can see all the moisture getting trapped in there. This is something that we call cold trap and allows us to actually capture the humidity inside the chamber. Now, this is not something that we do usually because we don't want moisture inside there. We want to have a clean environment so that we can go to high vacuum. There you go. Again, like I said before, we have the air, cold air actually being densified in contact with the coal mass. Now, as much fun as it looks, this is something that has to be done by professionals. You don't want to be touching this type of temperatures, specifically on metal. This will cause several damage to your skin, and it's not a good idea. This is a coal mass workstation. As you can see, we have the CRAT 900 3-chamber coal mass, which is identical to the ones you saw up there. This chamber allows us to have an absolute value of thermal conductivity, among other different applications. Right now, we have this material, which is multi-layer insulation that you can see in different applications like aerospace or even space vehicles. Right here, we got another type of cylinder called the CS200H. Now, this is very different to the ones we saw before because it's just one single chamber. So it is designed to do a different function, more basic, but it's still very impressive. Next, we have our custom-made unmanned aerial vehicle or drone applications. These work as well with liquid hydrogen and allows us to fuel the drones to be able to fly utilizing hydrogen. These are some of the many cold masses and tanks that the Kronstadt CS900 can utilize. What we do here is we prepare them for test, and then we take them up there when we actually perform it.
Currently, the largest liquid hydrogen storage tank in the world is across the river from us in Titusville. It's at NASA Kennedy Space Center. It is 1.25 million gallons in size. Plans for the future for running the world off of hydrogen include mega tanks of 26 million gallons and up, even bigger. But before one builds such a large-scale project as that, one needs clear data on all the engineering design attributes, materials, information that go into such a design. And with the Kronstadt 900 platform, we are providing the thermal conductivity test data on different materials that are essential to that sort of design effort. Mega-scale storage of liquid hydrogen is tied to the value chain and ability to get the price of production of hydrogen down. And in the US, we have a goal of $1 per kilogram by 2030. That's the goal. If that is achieved, then it's plausible that mega-scale tanks and global energy logistics can proceed. And it is that connection of A, the production, to Z, that application, putting all the links in the chain together that Gen H2 specializes in. It's a core, founding principle of how we operate is end-to-end and integral solutions, connecting ultimately renewable energy into the production of hydrogen in a clean and effective way.